morning all. Good morning all. A warm welcome to you. So today we have a privilege to host Dr. Gopalswamy from NASA Space Flight Center. He is one of the foremost space weather and solar physicists of present era in all eras. He has more than 23,000 citations, which speaks about his research potentials. So he is at present at NASA Goddard Space Flight Center. Before that, he was teaching in the University of Maryland as well. And he did his PhD in Indian Institute of Science, and then he was a resident research scientist in Coronal Solar Observatory. And now I will read out some of his accomplishments because it is very difficult to remember all of them. That much he has got. Some selected ones are he is the executive director of the International Space Weather Initiative, which is an international initiative which also runs several experiments in more than 100 countries. And he was past president of Scientific Committee on Solar Terrestrial Physics, which is a constituent body of COSPAR. COSPAR is one of the International Science Union's constituent body. He received numerous awards, including the 2013 NASA Leadership Medal, 2017 John C. Lindsay Memorial Award for Space Science, and American Geophysical Union's Space Physics and Astronomy Richard Carrington Award. He was awarded Doctor Honoris Causa by Bulgarian Academy of Sciences. Recently, in 2021, he received Lifetime Achievement Award from Eleven Science Foundation and Indian Science and Technology Association. And he is a fellow of the International Science Council and of the American Geophysical Union as well. So now he is going to take us to a journey on space weather. So I will invite him to give a very good talk. Please, sir. It's up to you now. And yeah, hope this works.
Thank you. Thank you, Natchimuthuk, for that introduction. I was not sure about the audience, and I took it that Natchimuthuk and undergraduate students are here. And so the level of presentation will be for seniors maybe a little bit too low, but bear with me. So what I'm going to talk about is how space weather affects life on Earth. Okay, so it's not like life was once killed by an asteroid, like dinosaurs were extinct. It's not that kind of interaction. It's more like if you have a huge flood in Chennai and you cannot do anything about it, right? So it's a disaster, and you have to cope with it. And that's that kind of disaster. The affecting life is more to do with the comforts that we have and how we lose it. For example, all of you use GPS for your navigation or maybe your time and everything. And that can be affected occasionally by events happening on the sun. You might have heard about transformers being burned, especially in the polar regions. And this all because of events happening on the sun. They produce huge currents encircling Earth, and that current is associated with the magnetic field. And then events on the sun, space weather events on the sun can produce particle radiation, high energy protons up to giga-electron volt. And those particles can come all the way to the ground, especially in the polar regions.
Last time, why was the problem? This time, Excel the problem.
I connected to Zoom.
Oh.
Just ask them to view
Problem.
So,
I think somewhere somebody has to be a problem.
Oh, it's online? No, you used to share your screen. You have to connect by Zoom and share it.
So this last topic we have for discussion. Sorry about this. Will definitely come in the end in whatever form.
Oh.
this is not. No, movie will be closed. Quantum.
And actually, that was your on that.
So we have done
Hello, Renu, where is room in the someone is
the
speaking?
CEOs, 8 after 7.
Seminar hall.
We have done national
Seminar hall.
9.
Immediate கொஞ்சம் சொல்லுங்க ஆஃபீஸ்
So you just connect your Zoom and then share the screen.
and this sounds from there.
It's not connected. So I'm just doing that.
I told them, and could you see if your mic is working now? Because when you put the volume off, it doesn't work. Right? And this mic is connected.
So you set the link around it.
Because something that is not very big.
Okay. Extend it.
Yes, yes. And someone is speaking. Someone is teaching.
Just reduce the sound.
No, sir, even channels are in. That's not problem.
So
Now it's switch up. No. Yeah, I get it's.
Sorry for online participants. Just now we have connected to Zoom. Now I'm sharing the screen. Is it visible? We should do now.
No.
you just share screen.
Yeah, it's already shared.
Okay. Okay. So
That should be fine.
Here it's not in full screen yet, right? Yeah.
So, somewhere online, if they can hear me.
Probably they are.
yeah, they should be fine.
They should be.
Okay.
Is it audible? Is it audible?
Okay. All right. So let's resume, and so I'm going to talk about space weather, and the keywords that you should be interested in are given in this box. So you might have heard about solar flares, which are energy released from the sun on a transient basis, and it can propagate to Earth in a matter of 8 minutes and affect Earth's ionosphere, because ionosphere is an important layer which is modulates our radio communication. It can allow high frequency waves to go above, and low frequency waves get reflected. And depending upon change in the ionosphere, these radio communications can be affected. And then you have coronal mass ejections, and you see a couple of examples on the right side. These stuff leaving the sun, some of them slow, some of them very fast. And the fast ones are associated with all these flickerings. And the flickering is nothing but energetic particles accelerated from near the sun in the solar corona, and they propagate to Earth. Often, if the energy is more than a giga-electron volt, they can reach the surface, so it's a Earth surface. And if you're taking a flight, passing through the polar regions, which is often there are many flights because it saves fuel to go over the poles. But if there's an event happening and the passengers and the crew get a huge radiation dose, that's because these particles come and hit the metal of the airplane and they produce a lot of secondaries. And then there's a huge radiation environment there. And these particles are basically accelerated by shock waves produced by coronal mass ejections. If an object moves with a speed exceeding the characteristic speed, it forms a shock, like sonic boom you might have heard about. But in the plasma, it is a different type of shock. It's called the magnetohydrodynamic shock. And then you have something known as coronal holes. These are low density, low temperature regions in the solar corona. And the magnetic fields there are open in the sense that they straight stream out from the sun and then particles can stream through them along the magnetic field lines. And so that represents a plasma wind which can have speeds anywhere from 300 kilometers per second all the way to more to 900 kilometers per second. Then associated with these events, you have geomagnetic storms. These are storms produced in the magnetic field of Earth. Right now we have Earth's magnetic field in front of us, depending upon which is it's north-south, right? But normally we don't feel it because it is immersed in a neutral atmosphere. But if you go to the ionosphere, then there's an interaction between the magnetic field and the charged particles. And if this magnetic field is disturbed, you have a lot of interesting phenomena going on, including the change in the ionospheric density, including the change in the temperature and density of the atmosphere, which has got direct implications for satellites, because the orbit of satellites depends upon a particular drag that is present in the atmosphere. If the drag goes up or goes down, then the orbit of the satellite is affected. So this is the domain that I'm going to talk about. So, and then because our technology depends
will
upon.
these be perturbations or will there be violent changes?
Well, indeed, they are perturbations in some layers, and they can be violent in some other layers. For example, on the sun, it is very violent, like the explosion I saw. And so in the atmosphere, it causes increase in temperature when an event happens, and that changes the drag. So I'll give you an example later on. You might have heard about in 2022, Elon Musk lost about 38 satellites because of this drag issue. There was a geomagnetic storms, and the atmospheric density went up, and then 38 satellites re-entered the atmosphere and burned. So that's how it affects. So how does it affect us? He was trying to put satellites up there so we can get internet, Starlink's internet from space, and that was got delayed basically. Of course, he has 4,000 satellites. It's only 1%. But still, it costs tens of millions of dollars. Right? So, I'm sure you all know what weather is, what climate is, right? And this is the famous quote, climate is what we expect, and weather is what we get. Right? So I'm talking about the weather aspect of it, but not the weather in the troposphere that we face outside, but it's more in space. Because in space we don't have neutral material like what we have in the atmosphere. Everything is plasma, and magnetic field are very important. And whenever you have plasma and magnetic field, plasma gets stuck to the magnetic field. So it's a basically short-term phenomena. And you saw the movie I showed. It's a series of images of the solar corona, where there is an explosion takes place. So explosion is basically a short-term phenomenon. But there are some long-term effects in space as well, because these events happen on the sun more frequently in certain periods. Every 10 years you have a solar cycle. Every 10 years, 11 years you have a lot of sunspots coming on the sun. And these sunspots are regions of high magnetic field. And as you know, sun is a ball of gas. And if you have magnetic field in a gas, then when the gas moves, because of all the convection going on, the magnetic field also pushed around. So field lines in this room, they're all fixed, not solid. But if it is in a plasma, the field lines can dance with the plasma. When the plasma moves, magnetic field moves as well. So in terrestrial weather, you already know what it is. It is conditions in the basically troposphere. You have high winds, hail, excessive rain or snow, wildfires. This all happen in this, but these all neutral atmosphere. But in space, we're talking about more plasma, and the domain of space weather is beyond the low layers of the atmosphere. You have can have space weather effect in atmosphere, ionosphere, magnetosphere, interplanetary space, and the sun. And we are worried about physical parameters like density, temperature, magnetic field, and then energetic particles. And the weather can be like the terrestrial weather. The weather can be normal, like if you go outside, it's nice. It may be a little bit hot. And sometimes it can become inconvenient, there's a drizzle or something. But then it can be dangerous also. So cyclones or hurricanes, they can disrupt life quite a bit. Similarly, in space weather is happening all the time. If you go to space, there is a particular density, temperature, they have small waves. But when there is an event, then all these parameters fluctuate heavily. So one thing space scientists are interested in is to predict these events. And once the events happen on the sun, how long will it take for the disturbance to arrive at Earth? And right now the prediction is accurate to plus minus 10 hours. So it's not great. But then weather has the terrestrial weather has been studied, from the beginning of last century, and people have really refined that you can just look at your cell phone and plan future. Right? It's going to rain there. What the temperature is going to be. It'll be very accurate, but very sophisticated because we have grid of observatories all around the globe. And then you take everything and push it in the computer, and then the computer produces the map. And every cell, what temperature, what cloud cover, possibility of rain and everything is predicted. But in the case of space weather, we don't have that much data. We don't have that much spacecraft, and the space is vast. So our state of prediction is more like what the weather prediction was in 1940s. But we are improving steadily. Okay. Also, the importance is growing because there are a lot of space activities now.
So prediction is by kind of a satellite which is kept probably at the L1 or something like that?
That is one of them. But we have a lot of other things. We have a lot of ground-based, for example, ionosondes. They can measure the density of the ionosphere. We have GPS signals passing through the ionosphere. There are instruments to monitor those signals. And monitoring that signals, you can figure
Those things will be after the event has taken place, right?
That's right, yes.
But whereas the L1 can say before it affects Earth itself.
Right. Before the event arrives at Earth, it can tell it, where it is coming from. So, in fact, most of the stuff I'm talking about is from Sun at L1. There is a spacecraft known as SOHO, Solar and Heliospheric Observatory. And this was launched in 1995. And it continues to work and produce beautiful imagery like the one I showed. Okay, so I don't have to tell you that the modern society is highly reliant on technology, especially space technology. So we rely on them for entertainment, communication, navigation, weather forecasting, precision agriculture, firefighting, and so on. There's so many ways we use space technology. Therefore, any of these are affected, life is affected. In fact, a lot of ATMs and banks rely on GPS signals. And if that system is knocked off, then imagine your entire banking system collapses. In some cases, the space weather events can derail a power grid. Okay, which you might have heard about. It happened in 1989 in Canada. So once you knock off the electricity, you cannot go and get your money from ATM. Okay. So then you can have a domino effect. And then you can have a big pipeline corroded. Railroads can be affected. It's all because of the global current system around the Earth, and that is modulated by the solar events. So, of course, one important aspect is the human exploration of space. Right now, we are doing mostly robotic, except in space station. That's the only place we have permanent human presence. In the future, soon, not very, very far into the future, we will have man on the moon, like a space station is staying there and working. So for those humans in space, we have to worry about particle radiation a lot. And right now they have some protection, but then it's always not possible. So then we go by the amount of dosage a person can have over lifetime. So they have to come down after a certain time. And finally, philosophical, I think I heard from Lakshmi that you guys do a lot of interdisciplinary stuff. So one interesting question you have to talk about it, what happens, there's too much crowded, we are not able to tolerate the politics, not able to, cohabit with all these ideas that we have to expand to some other place. There's not an easy place to go, we have to expand into space. Go to other planets, maybe from, at least from thousands of years from now, people can go to nearby star and find another Earth somewhere. So all these are possibilities you can think about. So you need to characterize the environment of other stars, what kind of habitable zones they have, and the knowledge that we gain from the sun and sun-planet interaction will be helpful in understanding what other stars may have, and the planets can be much closer, much farther away, depending upon the temperature of the star and what type of radiation it puts out. Okay, so I want to give you instead of giving you general ideas, I wanted to give a specific example. I already started this. This is the event of February 2022. When Elon Musk lost 38 satellites. And so what I have plotted here is the disturbance of Earth's magnetic field in the equatorial region. So normally when the Earth's magnetic field is quiet, it will be something like this. Maybe there's some small fluctuations, but more or less it's constant. What is plotted is the deviation from the standard magnetic field. Okay? So anything going away from zero means there is some disturbance of Earth's magnetic field going on. For example, here it is quiet, and here you see suddenly the field goes negative. That means Earth feels as if it has less magnetic field, horizontal magnetic field. And that is a storm. And it typically lasts for a few days. In this case, you can see it starts around and then it goes to 11 and maybe 12. So 2 days it lasts. So 2 days Earth feels as if it has less magnetic field and all the associated consequences. And Starlink was launched this time, and so there was a storm going on, and it was just getting recovery, and that's where it was launched. So this storm, very weak, so it's very about 60 nanotesla. That is the deviation. And 60 nanotesla is considered as a moderate storm. But even this moderate storm can kill 38 satellites. That's amazing. Right? It happened because they did not think about this. Okay, they assumed certain density. When you have a storm happening, during the storm what happens is the ionospheric current increases. So when the ionospheric current increases, that current can deposit energy in the atmosphere. It's called Joule heating. And once you heat the atmosphere, it locally expands. Right? So it's like you're running and suddenly you see some knee-deep water. Can you run with the same speed? You cannot. So you have some opposition. So the same thing happens when the satellite is moving in its orbit, suddenly the density goes up because of the storm, then the satellite feels a drag. And drag force is basically friction, and it will try to stop the satellite. So in low Earth orbit, if you want to keep the orbit, then you need to give energy. Right? You need to have fuel to keep the orbit. Otherwise it will fall. That's exactly what happened. And they will fall and burn. This is actually used as a technique to remove unwanted satellites and debris in space. So you deorbit them and they come a little bit down where the density is higher and they burn up. So we want that to happen for debris but not for the satellites. And this was caused by a very small mass ejection from the sun. This is the sun, and this is an occulting disk which makes an artificial eclipse. And that is the stuff, the white stuff you see, that is the coronal material that is being ejected from the sun. And it was not a very fast CME, it was only about 550 kilometers per second. So probably it can go to what, Bhubaneswar in 1 second, something like that, from here. So these are fast from our standards, but the speeds can be as high as 3,000 kilometers per second. And they can reach Earth in half a day. But most of them, are able between 1 and 4 days. So when we see something happening on the sun like this, and this is exactly the question you asked, this is an image taken from Sun Earth L1. So you probably know what Sun Earth L1 is. It's the gravity pull of the sun and Earth balance at that point. And that is about 1.5 million kilometers from Earth. It's very close to Earth compared to 150 million kilometers to the sun. And if you go there, because of the balance of these pulls, you don't need any fuel. The spacecraft can stay forever. And that's where it is sitting and monitoring the sun. And associated with this is a solar flare. This is in X-rays. So this curve represents emission from the sun in 1 to 8 angstrom wavelength. Okay. You divide by 10 to get the nanometers. And so this is a reasonably moderate solar flare and a mass ejection and a moderate storm. But these can be sometimes very big. And look at this one. So again, this is the zero line. And severe storms start from 100 nanotesla onwards. And look at this one. This is beyond the scale. It's looks like close to 600 nanotesla. It's 10 times bigger than what we saw last time. Okay. And this one happened the previous day. There was a big eruption of the sun, it started moving away from the sun with 1300 kilometers per second, arrived at Earth in about 30 hours. Then in Quebec, Canada, as soon as this mass ejection arrived at Earth, the transformer failed, burned. Then you have 6 million people lost power for almost a day in Canada. And if it's a cold time, of course, we don't care about losing power in the middle of the day or something like that. Of course, the AC will not work, but we can tolerate. But then in cold places, like in Canada, it's going to be extremely difficult. And this is the Quebec province in black. Can you cut this light up from here? So you can see that this entire province got affected, and then all the related effects. They will start driving to the US. Yes.
So just finish.
Yeah, go ahead.
So we find that there is this drop in the magnetic field strength, right?
Yes.
So what's the mechanism for that? So you have these energetic particles, they follow the field lines. Why is it that they cause a drop in the field and not a fluctuation of the entire magnetic field?
Right. So there is something called a ring current around Earth, and whenever you have a event happening and arriving at Earth, it enhances this current. So this current is associated with the magnetic field. Every current is associated with the magnetic field. It so happens that this magnetic field that is generated by this current is in opposite direction to Earth's magnetic field. So the vector addition gives you less magnetic field. That's all.
Why in the opposite direction?
Second,
Why is it the opposite direction?
that is just basically the rotation of Earth and then how the current positive charges move in one direction, negative charges move in direction. Current we measure using positive charges.
That is Le-Chatelier's principle. If anything affects things that
I
it's
see.
opposite.
Okay.
Yeah.
Okay. Oh, all right.
Okay, so that event is actually a landmark event because it really affected life. Now I wanted to show you this chart, which again gives you a little bit broader picture of what I said in the beginning. Okay, so this basically tells you about Sun-Earth connection.
Can I have a small question?
Yes, sir.
L1, how much time advantage it will give for any event of this kind for information on Earth?
Typically about 40 minutes, 30 minutes, depending upon the speed of the event. Typically less than an hour.
So a major event cannot be prevented even if information is available.
We can put a spacecraft in safe mode, don't operate and get in trouble. Okay, so this involves all kinds of physics, chemistry, particle physics, spectroscopy, and so many different fields are needed to investigate this domain. So the energy, of course, everything starts from the sun, and not only our sun. The main source of energy in the universe is basically thermonuclear fusion happening inside the stars. And this was proposed by Eddington in the 1920s, and Hans Bethe basically worked out the details of what kind of reaction rates happen inside the sun, stars. Of course, you have many different ways fusion can take place with elements up to iron, as you know, and iron kind of in the middle. So above heavier than iron, you have to have fission to, and then at lighter limits, they have to fuse. So normally this is below the iron atomic number. So for the sun, it's mainly protons becoming helium. That's the simplest process that happens, and that's good enough for the sun, and that's what is happening. And we know that now because every second there is a certain number of fusion reactions have to take place to produce the observed radiation we see. We can measure how much radiation we get, and to produce that radiation, how many reactions should take place per second. And we know that it is happening because of two things. One, of course, is the radiation. The other is neutrinos that are produced inside, and they come out, and each reaction has got a couple of neutrinos, and we know exactly how many neutrinos should be there per second. And in the beginning, people had problems reconciling because they have always observed less number of neutrinos than what theory predicts. This happened for maybe 3-4 decades, and finally there was a neutrino detector in Canada, and they found out that we are missing out a third of neutrinos because they change flavor before arriving at Earth. So now we know exactly it is happening inside the sun. And then, of course, this has the benefit that in the future, once we finish all the fossil fuels, we will be ready to do fusion on Earth. Of course, people have been testing for a long time, and that is something we learned from our sun, that we have a future energy source that we should focus on. And then you see all these color codes. So the yellow part represents the radiation we see. If you go outside and look at the sun, don't look at the sun directly without eclipse glasses, right? Because it can burn your retina. But the sun we see is just a nice brown disk in the sky. But in reality, the sun's atmosphere extends Earth and beyond the solar corona. So we are in the outer atmosphere of the sun. And we see all this electromagnetic radiation, and our eyes are sensitive to visible light, which is a very narrow in the electromagnetic spectrum, but we see electromagnetic radiation at all wavelengths, from radio to visible to ultraviolet, microwave, infrared, X-rays, gamma rays, all produced by the sun. And the solar corona is at 1,000,000 degrees, so a black body at 1,000,000 degrees will emit in X-rays. So if you have an X-ray telescope, you can image the sun, which is bigger than the optical sun, and it will be a couple of 1,000,000 degrees. So that's the electromagnetic radiation coming from the sun. And when there is a solar flare, that is an excess electromagnetic emission in addition to the normal quiet emission we get. But we also get a lot of wind and mass ejections. You already saw mass ejection going on. And this represents a release of billions of tons of material from the solar corona and taken into space. So this we call mass emission, because mass is ejected from the sun. That's transient. But there is also steady wind blowing from the sun. This is called solar wind. And it is the expansion of the solar corona. And it attains supersonic speeds and can go up to 900 kilometers per second. So this is another way sun is losing mass by mass ejections and by solar wind. And when Earth is in the path of these mass ejections, then all these geomagnetic storm and associated phenomena happen. But the mass ejections go in all directions from the sun, because eruptive centers can be all around the sun. Something can be happening on the backside of the sun going away from us, so we don't care about it unless we have a spacecraft sitting there. Then we have to worry about particle radiation hitting that spacecraft. So now the space weather has expanded not only for Earth but also into outer space, because we have assets in other parts of the heliosphere. For example, the Voyagers, they in fact left the solar system. They were launched when I was a graduate student in 1977. And, they've been working for so many decades. And fortunately, the designs were such that they were not affected, and they had this RTG power, so they did not depend upon solar panels. But we have many other spacecraft. I'll show you a picture later on, that we have so many in space right now. So this mass ejection chain happens because because of magnetic field generation in the outer one-third of the sun. So the energy is generated in the middle, in the interior, and the photons, what is released in the thermonuclear reaction are gamma rays, as you know. And these gamma rays, when they start propagating out, they hit all these dense material of atoms inside, basically hydrogen protons, densely packed, and they scatter these gamma rays, and they keep losing energy. So it takes almost like 1 million years for one photon to traverse from the center of the sun to the surface, and in that process it weakens. Weakens basically means the energy of the quantum decreases. By the time the photons of very low energy, they leave the sun. But in the outer one-third, the energy cannot be transported directly like radiation. So there is some convection sets in. So the outer layer voids. That convection, coupled with the sun's rotation, generates magnetic field. That's called the solar dynamo. And that magnetic field is what is causing all these space weather events. So the key to the space weather understanding is understanding the variability of solar magnetism. How the magnetic field is generated, why a lot of magnetic field is generated at certain times, and there is almost no magnetic field on the sun certain other times. And what happens between these two phases is what we are interested in. Okay, so that is the mass emission from the sun. And then we have the domain of geospace, that is Earth, atmosphere, ionosphere, microsphere, that's geospace. And with the geospace, all this energy flow comes in. For example, it causes, as I mentioned, the disturbances in the atmospheric density. It can affect the atmospheric chemistry. It can affect the ozone concentration. And then also you have a lot of things going from Earth upwards. Right? So there are big planetary waves, there are gravity waves, and that kind of disturbances in the atmosphere. And they go up and interact with the ionosphere. So there is an interaction between the neutral material and the ionized material. And that again causes density changes in the atmosphere. Even lightning produces electrons and positrons. And these particles can go up and modulate the density of charged particles. Finally, I have shown in red, GCR is galactic cosmic rays. So the galaxy contains billions and billions of stars, and there are also population of supernova explosions. You have billions of stars, they age and then explode. In that process, you produce a lot of charged particles. And these charged particles, they propagate long distance and then finally enter into the heliosphere. And they can penetrate through here. Cosmic rays. So these cosmic rays can be modulated by the mass ejections from the sun. These interplanetary coronal mass ejections, and they can modulate this because again charged particles can be deflected by the magnetic field. The same way Earth's magnetic field blocks a lot of this particle radiation. So all these are the variability that we see in the Sun-Earth system, and they can affect the even technology that we have in space and also on the ground. The current I was talking about in the ionosphere, they can also induce current on Earth under the surface. If you have, for example, a long pipeline, they can induce current in this pipeline. And if you have a current flowing through this pipeline, they can be corroded very quickly. Okay, so I want to give an example in the interplanetary space. Several years ago, almost 20 years ago, there was Japanese Mars mission known as Nozomi. You might have heard of Nozomi also, it's a bullet train, but this name was given to a Mars mission. And by the way, the meaning of Nozomi in Japanese is hope. And you can see the irony there. Hope becomes hopeless, right? So in April 21st of 2002, there was a big mass ejection. And that produced a particle radiation. So what is plotted here is the intensity of energetic photons as a function of time. So this is 21st. You can see when there is eruption happening on the sun, this is the background particle density we see mostly because of cosmic rays. And suddenly, the particle intensity goes up. Here it's actually gone out of the scale. So it's a factor of 10,000 to million. That's how the radiation intensity goes up. And then all the electronics and spacecraft can be affected by these particles. So think about a solar panel, you shoot a proton beam into it, it will destroy it. So these protons can do a lot of damages to spacecraft, solar panels, and the electrons can cause discharges on the surface of the spacecraft, interior of the spacecraft, depending on the energy. So this enhancement particle density lasted for, so here you can see 21, 22, this is 23, and for several days. For several days you have this disturbance, Earth is immersed in high particle intensity. And what you see in the bottom panels are basically the trajectory of the coronal mass ejection. And you get the also coincide, this is solar flare. And you can see solar flare, coronal mass ejection, particle intensity, they are really related. Big event happens, you know, many other things happening. And so these particles, of course, disable that Mars mission. So before getting into Mars, it became disabled completely. One interesting thing about space weather is that it doesn't care about a country. It's not Japanese, it can be India, it can be any country kind of thing. And so in 2003, just next year, they affected the US mission, it's called Mars RBC. And it had an experiment called the Mars radiation environment experiment. So the purpose of the Marie instrument is like a scouting trip. You know, they wanted to measure the particle environment of Mars. And in the process of measuring the radiation environment, the instrument was disabled. Because of another big event happened in 2003, you might have, that is termed Halloween storms because it happened in October, November of 2003. I'm sure you know about that. Halloween, it's a scary thing, right? And that really scared the people, and it was a huge set of events. And this shows that event. So it happened in the big sunspot region. Number 10486, that's the sunspot region. These are all sunspots, right? These are regions of seeds of eruptions. Because sunspots are regions of very high magnetic field. And energy is stored in the magnetic field. And it is released. We do not know when exactly it gets released, but we know it happens there. Because we know the solar gas is a plasma, magnetic field in a plasma is Chasulrano. Basically, the magnetic field is twisted and turned, and the energy is stored in the magnetic field. At a certain time, it cannot store anymore, and with a trigger, they explode. Very similar to you take a rubber band, you keep twisting it, right? At some stage, you release it, it jumps like a frog. So the kinetic energy it got is from the twisting. Similarly, magnetic field breaks up and then released, and you get this mass ejection. And so you can see from here, this is the same region, but then it is showing the solar flare. And this shows the mass ejection that was associated coming from here. And this is one stage, and this is another stage. So between this is about an hour, between here and here. And you can see this mass ejection has reached probably about 10 or 15 solar radii. Once we measure things in solar radius, one solar radius is like 700,000 kilometers. And in this one, compared to this one, you see all these dots again. That is because it took some time for the particles to be boosted up to high energies, and you have a particle radiation already showing up. So this is the intense particle emission that disabled the instrument. In fact, when they saw this increase in particle intensity, this is the particle flux per centimeter square per steradian per second, it's a function of time, and you see that it's going up to a very high level, and once the instrument sensed very high intensity, they put it in safe mode. And then after a couple of days, they wanted to revive it, never came back out. It was completely destroyed. And that is the explosion that killed it. It not only particle radiation, so this is the particle intensity as a function of time for several days from 26th October to 5th November, and that's why it's the Halloween period. You see that there are many events happening. It's not one event, compound event. So there is already density present in the atmosphere, and then this added up. And these are the two big events that you can see here. This is the first one, and then this is the second one. The second one looks actually not big because the first one created a lot of disturbances, so the contrast has changed.
So is this time frame of a few hours to a few days the typical time frame between spotting one of these, or between the explosion and the precursor to it?
Right. It's from the fastest that was observed is in 1972. When August 1972, when humans were active on the moon. Fortunately, that happened not when they were on the moon. It took 14 hours to reach Earth. And typically, it's more like 1 to 4 days. So it takes about 1 to 4 days, depending upon the speed. The fastest ones can come arrive in 1 day, and the slower one comes 3-4 days later. So you can think about 150 million kilometers and then 3,000 kilometers per second.
No, I don't quite mean the time for it to reach, but between having a sunspot
Yeah,
and having the explosion
yeah.
happen, what kind of time frame are we looking at then?
So when a sunspot explodes,
After we observe a sunspot forming,
right?
typically how much time does it take for it to actually explode?
That is a more than $1 million question. We do not know.
But a general time, a range.
So usually the sunspots, when they emerge, they start with a smaller one, then keep quickly expand within 1 or 2 days. They become fully formed, and then they start decaying. And decaying basically means that the positive and negative polarities are separating and dispersing. So sunspots usually for 1 or 2 rotations. That means a couple of months. That's the time scale over which they live. But the problem is we do not know when they erupt. That depends upon not only storage of energy, but also getting some kind of trigger to cut the magnetic fields. So that is one question people are right now working using AI, ML, observe some millions of sunspots happened in the past and try to feed it and let's see what pattern emerges. But right now, it is not easy to predict. But there are certain indicators like, if the sunspots are kind of squeezed together or pushed against each other or something like that, then it's easy. But still, it's not 100% sure thing. So we do not know when a sunspot appears, when it erupts. So that's a problem for young people to solve.
Do we have a theory for the formation of sunspots,
Yeah.
which is
Basically, they emerge from underneath because as I mentioned, because solar dynamo. So due to buoyancy, the magnetic field acts like a fluid. It has a pressure, right? So it becomes buoyant because the plasma density is low in the magnetic field, so they start rising and goes through the surface. So it's almost like a loop pushing through the surface. Then you have two legs. One is positive, one is negative. Now this is particle radiation. The other thing happened when these two mass ejections. See, it is called a halo CME because it seems to be surrounding the sun. By the way, this little white circle is the sun, and that is the occulting disk. We produce artificial eclipse to observe the corona. Because the corona is a million times dimmer than the photosphere. So what you see outside is very bright. Even if 0.1% of the sun is photosphere can be isolated, that kills the corona. You cannot see the corona because corona is a million times dimmer. But that's where all these things are happening. So that's why we need to put this occulting disk and block all this photospheric radiation so you can see the rest of the corona.
What is that? Is it a planet or a comet?
It's a planet. Now, another thing happened. When these two successively hit Earth, they produced two huge geomagnetic storms. You see, it's 400 nanotesla, right, compared to 60 nanotesla for the Musk event. And then there are so many things happened. In fact, there's a huge book that when I was working on this, I was asked to lead an effort to compile all investigations, and we have a big thick book of papers showing how various systems were affected by these storms. Now, these two magnetic storms, of course, one of the things is burning of a transformer, very similar to the 89 storm. And this happened in a place in Sweden called Malmö. And once again, millions of people lost power and so on. Yes?
Do the storms only affect places closer to the pole?
Yes.
Why is that?
Because as I mentioned at the beginning, Earth has a magnetic field. It acts like a what do you call a shield. But in the polar regions, the magnetic fields are open. They go into space. So it's easy for particles to propagate along open field lines. And they precipitate in the polar region. That's why you get aurora in the polar regions on both sides.
so we are safe.
Kind of, yes. But there are certain things happen in the equatorial region as well. They are known as geomagnetically induced currents. That can happen here as well. But we are protected from particles. Very well protected. Okay, and so this is the, your question anticipated this basically. So this is a plot of the electron density, column density, as a function of latitude, magnetic latitude. And you can see normally this is what the situation is. You have electron density like this, but when a storm happens, the density goes up by factor of several, and also it spreads to higher latitudes. This is due to a simple plasma process known as E cross B drift. If you have electric field and magnetic field in a plasma, you can lift the plasma, and the E cross B force acts upwards. So they lift the plasma, and the plasma, of course, has to fall back along magnetic field lines. The and they feel on both sides of the equator. And this kind of disturbance in the equatorial region can cause all kinds of problems or radio propagation. And this is also part of the same storm I showed in the previous pages. Okay, just a quick break from all this to tell you that these events can cause huge economic loss. For example, people have estimated millions of dollars of loss one of these events can cause. Okay. So I already mentioned that the seeds of these eruptions are the sunspot regions, and the sunspot regions. This is a magnetogram, and this is a continuum image. You can see each of these sunspot regions have bipolar magnetic field. The white is positive and dark is negative. So they are like a little distributed magnetic fields of the sun. And these are the regions where the energy is stored and released to produce these storms. And we call this dark side of the sun mainly because it's hazardous, and of course sunspots look dark if you put a glass and look at the sun. Okay, now I think running out of time, so I'm going to talk about this another aspect of the dark side of the sun. These are the coronal holes. So these are coronal holes, and this is the solar corona, what you see in color. And these are sunspot regions. Of course, sunspot regions in the corona, they look hot, high temperature and density. And these are regions of low temperature and low density. Okay. Now, these are holes because the magnetic fields in this region, they are unipolar, one polarity, either positive or negative. You can almost say that you have a sunspot region where the positive and negative separated far enough that they don't have memory of their connection between the two. Then you're getting unipolar regions. So the magnetic field actually starts from the sun and gets into space. Whenever you have field lines like that, the plasma streams along this magnetic field and leaves the sun. So that's basically because of the evacuation, you get this dark structure. And because of the open field lines, the plasma can go very fast, up to 900 kilometers per second. And then they are bumping into the previous wind, which is slower. Then they produce some kind of interaction regions. So they just hit and then they move like that around the sun. And this structure sometimes can hit Earth and cause geomagnetic storm as well. Because this compressed region has high magnetic field, and that magnetic field interacts with this magnetic field to produce the geomagnetic storms. I mentioned to you about magnetic energy storage. So this is again a sunspot, negative polarity, positive polarity, and the field lines connecting them. So if you look at these two pictures, these are actually satellite images with magnetic field, supermagnetic field lines computed and superposed. So here you can see that the field lines are twisted like an S shape, which is an indication of energy storage, non-potential. And once the energy is released, then they look like a potential field. That means the energy is found. The stored energy is released. So basically, this is a mechanism by which energy is generated in these mass ejections. Okay. So the mass ejections come and go during summer. They go. Cycle very similar to the sunspots. So we have to worry more about the CMEs during solar maximum. Right now we are in a solar maximum, almost very low activity, but still in solar maximum. So we have some idea. So this is one aspect of space climate, right? Long-term we know what to expect in solar maximum. You'll have more activities. So this is a subject of space climate, which I'm not going to talk about. Right. And then the mechanism of particle acceleration. So when you have a mass ejection coming out with supersonic or superalpinic speed, they accelerate particles, they stream out. And this guy, who passed away last year, Steve Taylor, he's the one who proposed the mechanism of this particle acceleration. So the CME drives the shock, and the shock accelerates these particles. Okay, so if you look at the speeds of this mass ejection that produce particle radiation, they're typically about 1500 kilometers per second. Average speed is about 400. So any high energy, high speed CME can drive a shock. Okay. And they are the ones which produce this particle radiation. Here's an example of, so this is the normal evolution of a current in a solar panel. Whenever you have a big event happening, photon and suddenly the current length decreases. The efficiency goes down. And these two events in 1989 essentially brought down significantly the power of a solar panel. So I just want to give you at least one example of how particle radiation can affect our solar panels. And then this is interesting for Lakshminarayan, so I just wanted to show this. So this represents a model of the polar atmosphere. So if you have one MeV proton coming from the sun, it can come only up to the top of the mesosphere, right, 7 MeV. If it is 10 MeV, it can come to the mesosphere. 100 MeV, it comes all the way to the stratosphere, where ozone resides. And these particles, when they hit the atmospheric molecules, they produce radicals, right? They ionize them. And these radicals, they go and interact with ozone, destroy ozone. So depletions like 4 or 5% is normal. And if it is very high energies, more than giga-electron volts, I mentioned in the beginning, they are the ones which affect flights. And these particles come all the way to the atmosphere. We can in fact observe them using ground-based instrument known as neutron monitors. I am almost done.
But that is very rare.
It happens, about a dozen times in a solar cycle, so of course once a year. But in the past 2 solar cycles, it's not happening much because the sun has very low activity. The sunspot number level, even in the maximum, is lower. So we have about 2 events per solar cycle. Okay, so I want to talk to you 1 minute about this process known as reconnection. When you have opposing magnetic fields come together in a plasma, they change the connectivity like this. Right? So the field lines, they were coming like this, and here it was going up. And once they connect, then they go like U-shaped, and they are pushed out with very high speed. In fact, that is the process which happens in the creation of mass ejections. The same thing can happen when the mass ejections come to Earth. They have this magnetic field. So this is the magnetic field of a mass ejection. And here it is represented by this huge circle. That's the magnetic field. Coming southward, Earth's field is northward, right? Because currently Earth's magnetic north is actually in the south. So the field lines are going to the north. So when the opposing field lines come together, then there is the solar field and Earth's field, they form a single field line. Then all the solar wind plasma enters into the magnetosphere and produce what is known as the ring current. The ring current sends particles towards Earth. They cause aurora, the ring current. And this kind of mass ejections are very high speed again, about 1,000 kilometers per second. once you have a geomagnetic storm, a couple of days later, you have a lot of spacecraft on the way. You can see this is the time of the onset of the storm, and a couple of days later, the spacecraft anomaly goes up significantly because you produce all these storms and extra particles, and these particles cause electronics to break down and so on. And these particle events can also affect the radiation belts. That's radiation belts, so that's Earth. And you have one inner belt and outer belt. Inner belt has protons, outer belt has electrons. And these can be severely modified when there is a storm. And sometimes the slot between the two belts can be filled with energetic particles. This, of course, people always start to worry about, because once you leave Earth with any spacecraft to outer space, you have to go through this belt, and you have to survive passing through that space. So we have to understand that. And I think I should point out this one other effect, which is sometimes the sun produces microwaves of very high intensity, and these microwaves can overwhelm the radio signals produced by the GPS satellites. So you basically lose the signal because the background goes up very high. This is called signal drowning. That can happen during solar flares. And this is one of the famous examples that happened in 2015. Again, in Sweden, the radars did not function because of GPS signals were all lost. All right, so I gave you got a glimpse of what we are dealing with, and we have so many spacecraft. So that's the Earth. The Magnetosphere is this thin lines. We have a lot of geospace missions, and then we have a lot of outer space missions. All these have got capability to monitor space weather, and also they have the potential to be affected by space weather. So we have a system of observatories from which we derive all this knowledge that I was talking to you. And of course, we have a lot more unanswered questions in this field. So there's a lot of progress to be made. And as I mentioned before, this knowledge that we gain from Sun-Earth interaction can be used for star-planet interactions in the future. So with that, I will stop. Thank you very much.